I was thinking just now, a few seconds ago, if I want to, it's better for me to give you a big picture of what lies ahead. That way you can contextualize what we're talking about today in your mind, and that way hopefully it'll help you better understand how does all this connect with each other. Okay, so the overall discussion is about linear optimization problems, and we're going to talk about what these are. But in this course, there are two general methods we use to conduct linear optimization. One of those methods is graphical. The other one is numerical. Again, the purpose of all this is to give you the big picture before we drill down to the fine details of each method. So to accomplish this, we can either do it graphically or we can do it numerically. The graphical method is called the geometric approach. And the numerical method is called the simplex method. Now, the geometric approach optimizes on both sides at the same time. That means it gives you the minimum and maximum points at the same time. But the numerical one, or the simplex method, you have to decide what you want to do from the outset, because those two methods, for maximizing something, a function, for maximizing a function, you would want to use one method, and for minimizing a function, you would want to use a slightly different method. But the main point being that the simplex method is numerical, the geometric approach is graphical, just like section 4.1, a little more than that, but just like that. And then together they can be used, either this or that, to optimize a linear function. There are also nonlinear functions that can be optimized, but that's not the subject for this course. Okay, so now that we discussed the big picture of what we're doing, let's see what are optimization problems to begin with. Okay, let's answer that question. So these are problems such that the solution demands us to either find the maximum point of that function or find the minimum point of that function, depending on what we're dealing with. That's what optimization means. Either find the minimum point or the maximum point. So let me write that down. Where the solution is either the maximum of the function. So where do we want to maximize a function? Well, if you have a profit function in business, you commonly have a profit function, you want to maximize it, right? So let's say that, such as a profit function. Either the maximum of the function or the minimum of the function. So where do we want to minimize a function? Well, if you have a cost function in running the business, you often do, you always do, then you want to minimize that function. So let's write that down, such as a cost function so is either this or that. So, and I want to underline the maximum and minimum, because that's what optimization is all about. You find the maximum and minimum of a function. Okay, so let's ask another question and answer it at the same time. We want to know what do optimization problems consist of? Okay. They have several components. Let's become familiar with those. We're going to be working with this for the next few sections. So they all have two or more variables. They all have a function to be maximized or minimized. And this function is called the objective function. So this function is called the objective function. Okay, and finally, if you inequalities that define any possible constraints. And these are called constraint inequalities. Okay, so now that we know what linear optimization problems are and what components do they have, then how do we use this particular method, the geometric approach, to solve a linear optimization problem? That's the topic of section 4.2 and 4.3. As a matter of fact, let me scroll down here and add here that for this, for the geometric approach, we're going to talk about that in sections 4.2, which is this one, and 4.3. Those are the two sections dedicated to this approach. And the numerical method, or the simplex method, for that we will look at this method in these sections, 5.1, 5.2, and 5.3. Okay, that's how the discussion is going to be about linear optimization problems. And after all this, we'll talk about probability concepts. Okay, so here we want to answer another question before we see examples. So how do we use the geometric approach, which is a graphical approach, right? to solve a linear optimization problem. So sometimes you might have heard the name linear programming. That's a name I don't use, but I want to just quickly mention it because if you see linear programming, that refers to the same thing, concept, linear optimization problem. But because, in my opinion, it's a misnomer because we're not going to program anything here on this content. It's just we're optimizing objective functions. In case you hear that name or see it somewhere, it refers to the same thing. Okay, so how do we use the geometric approach? Step one, there are several, everything we discuss in this course is highly procedural. So you master the procedure, you will easily master the content. So what are the procedures for this geometric approach? So step one, we want to establish the objective function. I say established because not always the objective function is given to us. Not always. If it's a purely mathematical problem, then yes, it's been given to us. But if we have a word problem, then we have to construct it. We have to introduce our own variables, and then we have to use those variables to construct the objective function. So that's why the first thing is we want to establish that. The second reason why we want to establish that, because the same variables that you use to set up the objective function are exactly the same variables you're going to need in your constraint inequalities. Over and over, I see people on exam, what they do on exam paper is they use different variables to set up the objective function and then a set of constraint inequality. They can't be different. The same variables that you use to set up the objective function should be exactly the same variables that go into the constraint inequalities. That's why establishing the objective function solidifies which are the variables you want to use in the constraint inequality or inequalities. Okay, so that's the first step. Step two is establish the constraint inequalities. So constraint inequalities come after this step, the establishing the objective function. Step three, we want to graph the constraint inequalities and this is what we learned in, you guessed it, section 4.1. That was the topic we did. This is why we learned in section 4.1 how to solve systems of linear inequalities. It's going to help us here. And then step 4. So once you find the solution region for this set of constraint inequalities, in that solution region, identify or find the coordinates of the corner points of the solution region. Okay, so these are the, so graph the constraint inequalities and then identify the coordinates of the corner points. You recall that in the previous section's video, at the last point, that's what we did, right? That system that we solved to get the coordinates of that one corner point that we didn't have. We're going to be doing that, if necessary, for the geometric approach. Sometimes it's not necessary to solve a system to get the corner points because they're all right there in front of us. Okay, so the next thing, the next step, so within a given context, you want to identify the feasible corner points. This is important because in the geometric approach, the method gives you all possible corner points for maximizing or minimizing a function, regardless of whether those points are feasible in a context. What is a context? A context would be given to us in a word problem. For example, if you want to maximize manufacturing a set of product, if one of the corner points for maximizing a profit is 0, 0, or the point of origin, if that's one of the corner points, then that's not feasible. That's not a feasible corner point, right? Because if you choose 0, 0, that means you don't have a business because you're not manufacturing any of the products. So some corner points, especially 0, 0, are not feasible for one reason or another. So we want to exclude those points when we go about optimizing a function, even though those points give us the minimum profit, but we don't want that kind of minimum profit because it means that we don't have a business. All right? Okay, and then lastly, so after step 5, we've identified all the feasible corner points, and the last step is to find the desired minimum or maximum value. Like that. Okay, so once we have the feasible corner points, simply plug them in to the objective function and see where the function has its minimum and where it has its maximum. Okay, so now let's see a few examples. Once again, let's start easy with an easy example, and then we'll build up on that knowledge. Okay, so here, well, let me first write down the objective function. This is the one, z equals x plus 6y. So in this problem, they want us to find the minimum and maximum values given a graph that I'm going to draw in a second. Not always a problem is asking for us to find the minimum and maximum. Sometimes they do. Mostly they ask us either for the minimum or maximum, but in this case we have to find both, which is just as easy as finding the other points for either minimum or maximum. Okay, so in this case, it turns out that we are given the graph of the constraint inequalities. We are not given the constraint inequalities themselves, but we are given the graph of them, or the solution region for them, which is fine. Okay, so let me draw that. Oops, my line is not straight like that. I meant for that to be the y-axis. I will bring my straight edge next time. Actually, I might have it. Let me look. I might have it. In fact, I do have it, so I don't know why I didn't remember this in the beginning, but yes. So let me correct this line. It should look neater than it is right now. Okay, that's a little bit better, like that and like that. All right, so we are given these points on this graph. We are given this point and this point and this point here and this point here. Okay, let's connect these points together. That. So once again, we are not given the constraint inequalities, but we are given the solution region. So a lot of the work has been done for us. Here's the solution region. And then let's label the corner points, right? So 2, 7 are the coordinates of that corner point. 2, 2 are the coordinates of that corner point. And this one is 8, 1. And that one is 7, 8. Okay, so given that, we're asked to find the minimum and maximum point of this objective function. It's easy. We're just going to plug in these coordinates for x and y in the objective function and see where z is minimum and maximum. So let's do that. I'm going to rewrite that objective function here so you can see it on the screen. Z equals x plus 6y. And the corner points are 4. So at 2, 7, at I'm going to go counterclockwise, 2 comma 2 at 8 comma 1, and finally at 7 comma 8, which is that point. Okay, so we're going to plug in z equals 2 plus 6 times 7, plugging into that. So we get 44 here, z equals 2 plus 6 times 2, and so that's 14. Z equals 8 plus 6 times 1 equals 14. Z equals 7 plus 6 times 8, so that's 55. Okay, so in this case, we have a maximum, right, at 7 comma 8, and we have a minimum at 2 points, which is okay. This sometimes can happen. So minimum at 2 comma 2 and 8 comma 1. So usually when I talk about this in a classroom where people are present, they ask me, well, what is the answer to this question? Well, the answer to this question is we have a minimum of 14 at 2 comma 2 and 8 comma 1, and a maximum of 55 at 7 comma 8. On a problem like this, in a paper exam or in an online exam, you can be asked about the maximum or minimum value, in which case you would tell 14 for minimum and 55 for the maximum, or you could be asked about where the location of the minimum and maximum points, in which case you would give 2 comma 2, 8 comma 1 for minimum and 7 comma 8 for the maximum point. Okay, so that's one example. Let's see another example. So we want to use the geometric approach to, this time, what do we want to do? We want to maximize. To maximize this objective function, z equals 5x plus 7y. Please note that for these purely mathematical problems, the objective function and the constraint inequalities are provided to us. That's not always the case. In section 4.3, which is next, coming up, we have word problems that will have us generate all of this, the objective function and the constraint inequalities. But for now, they are provided to us. So to maximize this objective function z, given the following constraint inequalities. So here are the constraint inequalities. Pardon me while I drink a little bit of water. Okay, so just like what we learned in section 4.1, we want to find, in order to find the solution region for this set of constraint inequalities, we're going to find each boundary line. We're going to test a test point to see which side is the solution of this one. We're going to repeat with this line and this line and this one, and then see where all solutions overlap. And then, because we're optimizing in this case, we're going to need to find the coordinates of the corner points. And then we can plug in those corner points in this objective function to figure out where we have a maximum. Okay, so we want to find this boundary line, this one. So we switch from inequality to equality in order to find the boundary line. And I'm going to use the intercepts again, x and y intercepts, to find this boundary line. So if x equals 0, then 3y equals 6, then y equals 2, which means we have 0, 2 as the y-intercept. If y equals 0 in that equation, 2x equals 6, which means x equals 3, or 3, 0 as the x-intercept. Okay, so first, before we go further, let's plot these 2 points. Notice from these 2 last constraint inequalities that everything is going to be positive. So I'm going to dedicate all of this blank space to the positive side of the axis, like that. And these are easy small numbers, right? So I'm going to make my increments large. Let's say 1, 2, and 3, and then 1, 2, and 3. Okay, so 0, 2 would be that point, and 3, 0 would be that point. Let's connect those with a solid or a dashed one. You guessed it, the solid line, right? Because of this equality that is under the inequality. And I'm going to write the inequality that is associated with this boundary line right on top of it, like that. Now we need to find a test point to see, is this side the solution of this inequality or that side? This line is not going through the origin, so I'm going to pick 0, 0 as my test point because it's such an easy point to test. So testing 0, 0 in this inequality, we get 2 times 0 plus 3 times 0 less than or equal to 6, 0 less than or equal to 6. Is this mathematical statement true? Absolutely it is true, right? So we picked a test point on this side of this line, which is that, and it checked out. So the same side as the test point is the solution of that inequality. All this region is the solution. I'm not making this shade darker than this because this is not our final solution, right? We're looking for the final solution would be the overlapping region. I will darken that one, but not this one. Just a few arrows would be sufficient. Okay, so the next line for us, the next boundary line for us to find is that one. X less than or equal to 2. Well, first of all, x equals to 2 would be the boundary line for that one, right? So let me draw that. It's going to go, x equals 2 is a vertical line that is going to go through right that x equals 2. So this is x, this boundary line is associated with x less than or equal to 2, right? That one. Okay, so for this one, we don't really need a test point. You can pick 0, 0 again, but it would be on this side. It's obvious that anything x values that are less than or equal to 2 are all on this side. So I'm just going to put a few arrows just to point in that direction, and we know that the solution for that one is on this side. So you can see a rough region of overlapping solutions, right? It's going to be in this region here, especially because everything has to be positive, x greater than or equal to 0. That means all the x values on this side are acceptable, and y has to be greater than or equal to 0. So all the y values that are pointing in that direction have to be part of the solution. So you put all of these individual solutions together. Where is the overlapping region? Well, the overlapping region, I'm going to thicken that boundary, is right here. It has a corner point there. It has a corner point here. It has a corner point here. I overshot. It has a corner point here. Then let's move up. It has a corner point here, and I'm going to make this a little bit thicker. And then it has that boundary line there, like that. So to make clear what our solution region is, let me make this darker. I trust that if you have questions, you will post them underneath the video on the discussion board. Right? Like that. Okay. So we found the solution region, but we're not just after the solution region, we're optimizing an objective function. So we need to find the corner points and then plug them into the objective function. So that one is already known. That one is already known. 0, 2 is one of the corner points. 0, 0 is a corner point. 2, 0, that's 2, 0 is another corner point. So 3 of them so far. And we have a 4th corner point right there. But right now, we don't know the coordinates of that. We need to find the corner point, the coordinates. That point is the intersection of this slant line and this vertical line, right? So let's solve that system. So maybe I can put that the coordinates of that here, up here. Maybe I should pick that. So one line is x equals 2. That's one of the lines forming that intersection. And the other one is this one, 2x plus 3y equals 6. That one, right? So that's an easy system to solve. We already know what 2 is, or x is. Plug it in here and find y. So let's do that. We have 2 times 2 plus 3 times y equals 6. 4 plus 3y equals 6. 3y equals 6 minus 4. 3y equals 2. Y equals 2/3. So the coordinates of that last point are 2 comma 2/3, right? So we have 4 corner points and we have the coordinates of all 4 corner points. We can plug into the objective function. I'm going to have to scroll up the graph, but I'm going to write everything down here so you can see what we're doing. So our objective function is z equals 5x plus 7y. We're maximizing this. And the corner points are, I'm going to go counterclockwise again, 0, 2, and 0, 0, and 2, 0, and 2, 2/3. Okay, so let's plug in. We have z equals 5 times 0 plus 7 times 2, that's 14. And this is just 0, right? 0. And then z equals 5 times 2 plus 7 times 0. So we have 10. And then z equals 5 times 2 plus 7 times 2 over 3. So what do we get? We get 10 plus 14 over 3. And so if we take the common denominator here, this is 1, and so the common denominator is 3. 14 over 3, it's already there, so we don't need to multiply this by anything. But 10 over 1, we need to get this denominator to be 3, so we should multiply this by 3 over 3, the numerator and the denominator, just to get this 10 to have a denominator equal to the common denominator. So that way we can add the numerator, right? If the denominators are common, we can easily add the numerator. So 3 times 10 is 30, plus 14 is just 14, and we get 44 over 3. So 44 over 3, I have it here in my notes, that is equal to roughly, after rounding, 14.67. And compare this with these other numbers that we found from each corner point. Clearly, this is or slightly over that, right? So this is the maximum point. So maximum value is 14.67, or 44 over 3 to be exact, and that happens at that point that we found, 2, 2/3. So if they ask us what's the maximum value, we know it's 44/3. That's actually, I'd rather you guys give the answer like that. Okay, because this one is not exact. That's exact. 44 over 3 is exact. So that's an exact answer. And then if they ask you where does it happen, you can just enter this this set of coordinates. Okay, so that's one example, or the second example. Let's see another example before we wrap up this section. Okay, so this time we want to use the geometric approach. This time we want to minimize the system. So previous example was maximize. This is to minimize, right? Minimize the objective function subject to constraints, and these are the constraints. To these 5 constraints. Okay, so just like before, we need to find the boundary solution, pick a test point on either side, doesn't make any difference, find which side is the solution of this inequality, do the same thing with this one, with all of these, and then see where all of these guys overlap. That solution region is gonna have to have some corner points, right? Make sure that we find or identify all the coordinates of the corner points and then plug those corner points here to see where this function is minimized. So let's do that. I'm going to begin with this one first. And notice right off the bat, because the final 2 constraints are telling me that everything is going to be positive, so I'm going to draw my axis for the graph such that all of that blank space is given to the positive side. All right, so let me draw it right away, and that way we can plot our points and draw our lines as we go along, like that. So that's x, and then let me move this as high as I can, like that, and this is y. Okay, so let's begin with the first one. I'm going to use up this space here, the blank space. So x plus y equals to 2. Then if, I'm going to use the intercepts again, if x equals 0, then y equals to 2 from here. Therefore, 0, comma 2 is the y-intercept. And if y equals 0 in that equation, then x equals to 2, and then therefore 2, comma 0 would be the x-intercept for that. So we will have some 12 is much larger than 2 and 3, so I'm going to have to increment my axis so I can fit all of this along the axis. I think if I start here, I should be able to get all 12 increments there. Let me try it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Like that. And let's do the same thing here. I'm sure I'm off here, but it's okay. My increments aren't as equal as that. Like that. Okay, so let's plot 0, comma 2 and 2, comma 0. 0, comma 2 would be there. 2, comma 0 would be there. And these are all solid lines, right? Because we have equality, equality, equality. So let's connect those 2 points like that. And I'm going to write down next to this the inequality that is associated with this boundary line, which is x plus y greater than or equal to 2. Okay, so let's pick a test point. Testing, notice that this line is not going through the origin, so we can pick that point, the origin, as a test point. If it did go through the origin, then we couldn't test origin because we already knew that it would be on the line. So picking, if a line goes through the origin and you pick 0, 0 as a test point, it's not going to provide you with any information about the solution, right? Because you are on the line, you already know where the line is. So you don't want to pick a point that is on the line. You want to pick any point that is off the line so you can plug it in and see if this inequality checks out. That's the idea, basically. So in this case, we can, and after plugging into that, we get 0 plus 0 greater than or equal to 2. No. So this doesn't make any sense. So the test point was on this side, right? And it didn't check out. So the other side must be the solution. So that, I'm just going to put 2 arrow lines like that. So let's now find the boundary line for this one. You can barely see it at the top. X plus 3y less than or equal to 12. So we're going to write it as an equality to find the boundary line. Once again, I'm going to use the intercepts. If x equals 0, then 3y equals to 12, and then y equals to 4. So 0, 4 is the y-intercept. If y equals 0 here, then x equals 12, therefore 12, 0 is the x-intercept. So let's plot these 2 points on the axis and draw the line through them. 0, 4 would be that point here, that one. 12, 0 would be that point. And let's connect those 2 points with a solid line, right? Like that. And so I'm going to write down the equation of this line. Well, let me write it here, or on top of it somewhere here. So x plus 3y less than or equal to 12, because this graph is going to get a little bit crowded, and so we want to be able to find the boundary lines and which inequality they're associated with. Okay, so now that we have the boundary line figured out, then we need to let's see, find the region of solution for that one. So this line isn't going through the origin. We can use the origin as a test point. So testing, well, I'm going to use, I'd rather use all my blank space, so I'm going to use this, or well, if I use this space, I might confuse some people, so I'm going to use it here. So testing 0, 0, what do we get? Plugging it into this inequality, right? We get 3 times 0 plus, so we get 3 plus 3 times 0 less than or equal to 12. Definitely, well, let's see what happened here. So that is 0. Sorry about that. So x is 0 plus 3 times 0. So we end up with 0 less than or equal to 12, which is correct. So the same side as the test point, which is this side, checks out, is the solution of that one. Okay, So we have a third inequality. Let me write that here. It is 3x plus y equals to 12. Let's find this boundary line. So if x equals 0, then y equals to 12. So we have 0, comma 12 as the y-intercept. If y equals 0, then 3x equals 12, and then x equals 4. Therefore, we have 4, comma 0 as the x-intercept. So these 2 points are our intercepts. So let's plot it. 0, comma 12 would be way up here. That's 0, comma 12. And 4, comma 0 would be this one. Let's connect those with a solid line like that. And I'm going to write on top of this the inequality that is associated with it. So 3x plus y less than or equal to 12. Okay, so let's pick a test point. Again, this line is not going through the origin, so we can pick the origin as a test point in that, right? And as a test point for this inequality. So testing 0, comma 0, what do we have? We have 0, plug it in there, 3 times 0 plus 0. Is it less than or equal to 12? Absolutely. So it checks out. So the same side as the test point for this line is the solution of that inequality. And then, of course, the last two inequality, these last two tell us that keep everything positive. So let me use my thick marker to identify the solution, the boundaries of the solution region. So we can't go to the negative side, right? Because of x always being greater than or equal to 0. So this is a boundary line right there. Those are 2 corner points. Then this line, there is no overlapping here of all solutions. So this line turns this way. Then there is a corner here because of this condition, y greater than or equal to 0, we cannot dip in the negative y territory. So we come this way. There's a node here. Then we go, the line goes this way. There is a node here, or there's a corner point there. And then, of course, we have a boundary right there. So the solution region is here. Okay, that's the solution region for this problem. Because we're optimizing, or minimizing in this case, we can't stop here. We need to find the coordinates of all of these 5 corner points and then plug it into the objective function, which is up here. So this corner point we already know, right? That's 0, comma 4. Let me write that down here. That's one of the corner points. This one we also know. It's 0, comma 2. Then this one we already know. That's 2, comma 0, right? This one we also know. That's 4, comma 0. And then finally we get to this point. We don't have the coordinates of that yet, but last section, at the end of the last section, we talked about how to do that, right? And the previous example And we kind of did that, but that wasn't a really easy one. So let's find the coordinates of that point. We need to do that. So that point is the intersection of two lines. This one, which has that equation, if we replace this inequality with an equality, it would be x plus 3y equals 12, right? That's that. And this line, these two lines intersect each other at that point to form that corner point. And the equation of that line, this boundary line, is 3x plus y equals to 12. Okay, so now we do know how to solve a system of two equations, two unknowns. Let's do that. So either variable is just as easy to eliminate. I'm going to multiply the top equation by -3 to get rid of the x terms. So -3 here. Then we'll get -3x minus 9y. Don't forget to distribute this to both sides. Minus 36. And then 3x plus y equals 12. Let's add those two equations. The x terms drop out as we intended. Minus 9y plus y. That's positive 8y. Negative 8y. Sorry about that. Negative 8y equals minus 36 plus 12, it's negative 24. So y is equal to 3. Okay, so we have 3, y equals 3. To find x, we can simply substitute for y in either of these two equations and solve for x, right? I'm going to use the first equation. So using x plus 3y equals 12, we have x plus 3 times 3 equals 12. And then we have x plus 9 equals to 12. So 12 minus 9 is equal to 3. So lo and behold, the coordinates of that corner point are 3, 3. Right? 3, 3. So that's the last corner point we wanted to know about. Let me write it here. Like that. Okay. So I'm sure you have questions about this solution. Please don't forget to type those questions or bring them up on the discussion board right underneath the video. Okay, so now we have our objective function given to us up here. Let me write it down here so it's in front of us. Z equals 2x plus 3y. We want to minimize this. Okay. So z equal, plug this into that. 2 times 0 plus 3 times 4. We end up 0 plus 12 is 12. Z equals 2 times 0 plus 2 times 3. And that's 6. And next one, z equals 2 times 2, right? Just plug for x with 2 from this point, and for y with 0. Plus 3 times 0, we have 4. And then for 4, 0, z equals 2 times 4 plus 3 times 0, and we get 8. And finally, for this one, we have 2 times 3 plus 3 times 3, and we get 6 plus 9, we get 15. So we're looking for minimum point. It's certainly that one, right? That's the point of minimum. So at 2 comma 0, there is a minimum value equal to 4. So if they ask you what's the maximum or the minimum value, you say 4. If they ask which corner point, where does this minimum happen, you give the coordinates of 2 comma 0, parentheses 2 comma 0. All right, so this wraps up our discussion of optimizing problems using the geometric method. When we come back next time, we will apply the same method to solving word problems. Word problems are not difficult at all once you know how you should approach them. So that'll be the topic of section 4.3. So for now, have a nice day, stay safe, and join me in the next video later.